Everyone, welcome back to the channel. If you've ever thought about getting certified in Databricks or stepping up your data engineering game, this video's for you. Today, we're breaking down everything you need to know about the Databricks Certified Data Engineer Professional exam. And trust me, by the end of this, you'll know exactly what to expect, how to prepare, and what it takes to ace it. All right, let's jump right in. What exactly is this certification all about? Well, in simple terms, this is Databricks' advanced level certification for data engineers who already have some experience building real-world pipelines. It tests your ability to use Databricks for serious production-level tasks, things like creating optimized ETL pipelines, modeling data for a lakehouse, and making sure your data systems are secure, reliable, and monitored before deployment. Now, this one's really interesting. Like, the exam doesn't just check whether you know a few Spark commands or can drag and drop in the Databricks UI. Nope. It actually goes deep into how you think as a data engineer. Can you transform raw, messy data into something that's ready for analytics? Can you tune performance when jobs start running slow? And can you ensure your pipelines scale as data grows? That's what this certification is really testing. You might be wondering, okay, what kind of tools and topics are covered? Let's break that down together. You'll need solid knowledge of Apache Spark, Delta Lake, MLflow, and even the Databricks CLI and REST API. So this isn't just about theory, it's about being hands-on with the platform. You'll also be expected to understand data modeling concepts in the context of the Lakehouse architecture, which means knowing how to organize data efficiently for both batch and streaming workloads. And speaking of streaming, Databricks streaming and Delta Live tables play a huge part in this exam. That's why Databricks actually recommends a self-paced course called Delta Dawn, which walks you through how streaming data is managed and transformed using Delta Live tables. All right, so what's the exam format like? Here's where it gets real. You'll face 60 multiple choice questions, and you'll have 120 minutes to finish. That's 2 full hours. It's an online proctored exam, meaning you can take it from home, but someone's virtually watching to ensure no unfair help. And sorry, no notes or aides are allowed. The registration fee, $200 USD, plus taxes, depending on where you're located. Now, hang on, because this part's super important. There are no official prerequisites to take the exam, but Databricks highly recommends at least 1 year of hands-on experience. That's because you're expected to be familiar with the platform's ecosystem, from notebooks and jobs to workflows and data pipelines. And one thing a lot of people don't realize is that the exam includes unscored content, basically a few test questions that don't count toward your score. They're just there to collect data for future exams. You won't know which ones they are, but don't worry, extra time is already factored in for those. Now, so what does this really mean for you if you pass? Well, earning this certification proves that you can handle advanced real-world data engineering tasks using Databricks. It sets you apart from the average Spark developer because it shows you understand not just how to process data, but how to design for reliability, scalability, and performance. Plus, it's valid for 2 years, after which you'll need to recertify by taking the full exam again. So, if you're serious about a career in data engineering, this certification is absolutely worth it. It opens up new roles, helps you speak the language of big data teams, and gives you credibility in one of the fastest growing ecosystems out there. So now let's look into the first question. A Databricks engineer needs to ensure that deleted PII data in a Delta table is permanently removed from cloud storage while maintaining historical audit capabilities. Which strategy satisfies this requirement while aligning with GDPR and CCPA guidelines? Please listen carefully. I'll read all options first. Option A, perform a delete operation on the Delta table, then run vacuum with a retain period that matches the required audit and retention policies to remove unreferenced data files permanently. Option B, directly drop the Delta table containing the PII data without using vacuum, and rely on Delta Lake to automatically remove all historical files from cloud storage. Option C, only mark rows containing PII as is deleted equals true and retain the data files indefinitely to maintain audit trails without any deletion or vacuum operation. Option D, delete the PII columns in place using alter table drop column commands, while leaving the rest of the table untouched to preserve non-PII data. Okay, that's all 4 options. Let's pause for a second. Let's look into the first question here. Which one actually satisfies both permanent deletion from cloud storage and auditability requirements under GDPR's CCPA? Now, this one's really interesting because on the surface, a few of these approaches could seem to work, but the devil's in the details. Let's break that down together so you can see the implications of each choice, and then I'll tell you which one is the right strategy and why. First, some context. Delta Lake uses versioned metadata and underlying Parquet or other data files. When you perform logical operations like delete or drop column, Delta records a new table version that excludes the data logically, but the old data files still exist in cloud object storage until they're physically removed. That's important because privacy regulations like GDPR and CCPA require that personal data be actually removed when deletion is requested, subject to allowed retention/audit windows. Also, teams often need to retain historical auditability for a specified retention period. Now let's walk through each option briefly and then conclude. Option B suggests dropping the entire table. You might think dropping a table removes everything, but this is risky. Dropping the table removes all data, not just the PII, and can destroy necessary non-PII historical records you must keep for audits or operations. It's also heavy-handed and rarely acceptable in production. Option C says just mark rows as is deleted equals true and keep files indefinitely. That preserves audit trails but leaves PII physically present in cloud storage forever, which is inconsistent with deletion requirements from privacy laws. So that doesn't meet the permanently removed from cloud storage requirement. Option D suggests using alter table drop column. That removes columns from the table schema, but it doesn't guarantee the underlying Parquet files are scrubbed or removed immediately. Because of Delta Lake's file versioning, previous file versions may still contain that PII, so this by itself is insufficient for permanent deletion. Option A combines 2 operations, a logical delete to remove the PII records from the table's current state, followed by vacuum to purge unreferenced data files from cloud storage. Here's why that matters. Delete creates a new table snapshot excluding PII, but vacuum is the mechanism that physically deletes the unreferenced files. The vacuum operation supports a retain period, and this is the critical control. You set the retain period to match your organization's audit and retention policies. For example, a retention window required for forensic or regulatory audits. During that retention window, historical versions are still available for auditing via time travel. After the retain window passes, vacuum will permanently remove the unreferenced files, ensuring PII is gone from cloud storage. Hang on, because this part's super important. Do not set the vacuum retain period shorter than your legally required audit retention. Many teams default to Delta's safe defaults like 7 days. That's to prevent accidental data loss, but compliance teams will often require a longer retention window. Align the vacuum retain time with your documented retention audit policy, add process controls, and verify deletion by checking cloud storage for removed files if audits demand proof. So, what does this really mean for you? Use the delete vacuum pattern and configure the vacuum retain period to match policy. That approach provides both true physical deletion after the allowed audit window and historical auditability during the retention period. Correct answer, option A, perform a delete on the Delta table, then run vacuum with a retain period that matches audit and retention policies to remove unreferenced data files permanently. Okay, so now let's dive into the second question. An organization is planning to implement Unity Catalog in Databricks to manage both structured and unstructured data, as well as AI assets like ML models and feature tables. They want to ensure that the data governance model they choose allows teams to operate independently within their data domains while maintaining overall compliance. Which governance approach best suits this scenario? Please listen carefully. Here are all the options. Option 1. Centralized governance, where administrators control the metastore and have full ownership of all assets and permissions across the organization. Option 2, distributed governance, where each data domain has its own catalog and owners of those catalogs manage assets and governance independently of other domains. Option 3, hybrid governance, where all assets are managed centrally, but access control is delegated to individual teams with read-only permissions. Option 4, federated governance, where each workspace has separate Unity catalogs with no central oversight and no ability to share metadata between teams. Okay, that's all 4 options. Let's pause for a moment. Let's look into the first question. Which approach actually allows teams to operate independently while keeping governance and compliance intact? Now, this one's really interesting because governance can sound straightforward, but the right model depends heavily on how your teams and data domains operate. Let's break that down together. So let's think about what we need. The organization wants independence for teams, clear ownership, and overall compliance. That rules out a fully centralized model. Centralized governance. Option 1 puts all control in the hands of a few administrators. Sure, it ensures strict compliance, but it can create bottlenecks. Teams need to wait for approvals to manage their own assets, which slows down innovation, especially when dealing with ML models or feature tables that require frequent updates. Option 3, hybrid governance, might sound like a compromise, but here's the tricky part. Delegating read-only permissions centrally can quickly become messy. Different teams might interpret policies differently, creating inconsistencies in access enforcement. That can introduce risk and complicate audits. Option 4, federated governance without any central oversight, sounds very independent, right? But without central visibility, you lose the ability to track metadata, lineage, and security policies across the organization. Redundancy and compliance gaps can easily creep in. So what does this really mean for you? The best fit here is option 2, distributed governance. Hang on, because this part's super important. In distributed governance, each data domain has its own catalog. The owners of that catalog can fully manage assets and governance within their domain. This reduces bottlenecks, keeps operations autonomous, and still maintains compliance because each domain knows and enforces its rules. Plus, Unity Catalog supports this model beautifully, whether you're managing structured tables, unstructured datasets, or ML assets and feature tables. Teams can operate independently without stepping on each other's toes. Distributed governance also makes auditing and policy enforcement more straightforward. Each domain maintains consistent metadata and access controls, which means when auditors come knocking, everything is clear, traceable, and compliant. So let's recap. Centralized, too slow and bottleneck prone. Hybrid, too complex and inconsistent. Federated, without oversight, too risky. Distributed, autonomy for teams, clear ownership, and strong compliance, a perfect balance. And that's why, if you're setting up Unity Catalog in Databricks, distributed governance is the way to go. All right, that wraps up this breakdown. I hope this helps you understand not just what governance model to choose, but why it matters for both productivity and compliance. Now let's look at question number 3. A data engineer is tasked with tracking the full lineage of datasets and AI models in Unity Catalog to improve compliance, data quality, and debugging processes. Which of the following actions would most effectively support these objectives? 1. Track dataset transformations, capture source and downstream tables, and monitor which notebooks, jobs, and dashboards interact with the data. 2. Apply row filters and column masking to all tables to ensure data security and restrict unauthorized access to sensitive fields. 3. Grant all privileges on all catalog objects to the data engineering team to ensure they can make unrestricted changes and capture metadata events. 4. Store all data assets in multiple metastores across regions to increase visibility and provide redundancy in case of outages. Okay, now that we've seen the options, let's break this down together. Let's start with option 1. This one's really interesting because it hits right at the heart of data lineage. Tracking dataset transformations, capturing metadata about sources and downstream tables, and monitoring which notebooks, jobs, and dashboards interact with your data. This is exactly what gives you a clear picture of how data moves and changes over time. Imagine you have a dataset feeding an AI model. If something goes wrong, like an unexpected result or a quality issue, you can trace it back step by step. You can see where the data originated, what transformations were applied, and what downstream reports or models it impacted. This is huge for compliance too, whether you're dealing with GDPR, CCPA, HIPAA, or SOX. You get an audit-ready trail that shows exactly how data was handled, which is a lifesaver for both governance and debugging. Now, option 2, applying row filters and column masking. That's important for security, no doubt. It helps prevent unauthorized access to sensitive information. But here's the catch. It doesn't actually help you track lineage. You still won't know how your datasets flow through pipelines or which jobs or dashboards are impacted by changes. Security and lineage are related, but they're not the same thing. Option 3 is a little tempting at first glance. Granting all privileges on everything. Sounds like ultimate control, right? But you might be wondering why that's risky. Well, it opens up the system to uncontrolled changes, which is exactly what governance and compliance frameworks try to prevent. You could lose visibility on who did what, which totally defeats the purpose of tracking lineage. Finally, option 4, storing data in multiple metastores across regions. Sure, this can help with redundancy and maybe a bit of visibility, but it doesn't inherently track how your data is transformed or used. You might increase availability, but you won't get the insights needed for impact analysis or debugging. So, what does this really mean for you as a data engineer? The key takeaway here is that proper lineage management is about visibility and context. By tracking transformations, capturing upstream and downstream dependencies, and monitoring interactions across jobs and dashboards, you gain operational efficiency, reduce errors, and ensure governance over both data and AI models. It's not just about storing data or locking it down. It's about understanding its full journey. So here's the question number 4. You're running a continuous Lakeflow job and you notice repeated task failures. Now, the big question is, which strategy aligns with Lakeflow's recommended approach for handling retries efficiently? Let's look at the options together. Leverage the exponential backoff feature in Lakeflow jobs, monitor the consecutive failures counter, and if needed, click Restart Run to reset the retry period while ensuring cluster resources are sufficient for the next attempt. Immediately delete the job run history and start a completely new job to prevent exponential backoff from delaying retries. Manually increase the maximum concurrent runs for all tasks without checking cluster resource availability to guarantee retries succeed. Disable monitoring and wait for the tasks to eventually complete successfully without intervention, assuming that repeated retries will eventually resolve the failure. All right, now that we've seen the options, let's break this down together. Let's start with option 1. This one's really interesting because it aligns perfectly with Lakeflow's built-in mechanisms. Exponential backoff might sound fancy, but it's actually pretty straightforward. When a job fails repeatedly, Lakeflow automatically increases the interval between retries. Why does it do this? Well, if you keep hammering the cluster with retries every second, you're basically asking for more failures and resource exhaustion. By spacing out retries progressively, the system gives itself some breathing room, avoids overloading resources, and increases the chance that the next retry actually succeeds. Now, you might be wondering, okay, but what about intervention? When should I step in? That's where the consecutive failures counter comes into play. By monitoring this counter in the job details panel, you can see if something is going wrong repeatedly. If needed, you can click Restart Run. This cancels the active run, resets the retry period, and starts a fresh attempt, all while making sure your cluster has enough resources to handle it. It's like giving the job a fresh shot, but in a controlled, resource-efficient way. Option 2 might seem tempting. Delete the job run history and start fresh. But here's the thing. That actually bypasses the exponential backoff. You're not addressing the root cause of the failures, and you might end up hitting the same issue repeatedly, just faster. Option 3 is also risky. Increasing the maximum concurrent runs without checking cluster resources might sound like a quick fix, but it's like overloading a server with too many tasks at once. Guaranteed chaos. You could actually make failures worse. And option 4, well, just ignoring the problem and waiting for tasks to complete is almost never a good idea. Repeated failures without monitoring waste resources and time, and you have no control over when or if the job will succeed. So what does this really mean for you? Exponential backoff isn't just a fancy feature, it's your friend. It helps keep retries under control, protects your cluster, and ensures job stability. By monitoring failures and intervening intelligently when needed, you maintain efficiency and avoid unnecessary resource consumption. All right, friends, that's a wrap for today. If you're working with Lakeflow jobs, remember, exponential backoff plus careful monitoring, happier pipelines, and less headache. Let's look at question number 5. Imagine you're on a project team and you need to deploy a streaming workflow that reads from a bronze layer, transforms data into a silver layer, and then drives dashboards on the gold layer. Pretty standard medallion architecture stuff, right? But here's the twist. You want to manage everything under a fully managed asset bundle. That means streaming configuration, notebook references, trigger semantics, the whole package. So, which Databricks asset bundle resource is designed specifically for this? Let's dive in. All right, here are the options we're looking at. Option 1, the job resource is solely responsible for handling continuous streaming semantics without requiring a separate pipeline declaration. Option 2, the cluster resource automatically converts batch jobs into streaming pipelines if configured with streaming settings. Option 3, the database catalog resource can be extended to manage a stream processing logic and state transitions during deployment. Option 4, the pipeline resource is designed to define and deploy streaming workflows with transformation logic and data flow, orchestration. Okay, now that we've seen the on together, let's break it down. Let's start with option 4, the pipeline resource. Now this one's really interesting because it's actually built exactly for this purpose. Pipelines in Databricks, especially when you're using Delta Live tables, let you orchestrate transformation logic from bronze to silver to gold. That means you can define continuous or triggered processing semantics, all declaratively, right in the resource configuration. It's like having a blueprint for your streaming workflow. Everything from the data transformations to scheduling and even quality enforcement rules can live in that single pipeline resource. And here's the cool part. Pipelines integrate cleanly with dashboards, so your gold layer outputs are immediately ready for visualization. Option 1 is the job resource. Now, jobs can definitely run streaming code, but here's the catch. They don't give you the full orchestration capabilities or the declarative lineage that pipelines offer. If you use jobs alone, you're missing out on that structured way of managing transformations across bronze, silver, and gold layers, and you might end up writing a lot of glue code just to handle triggers and dependencies. Option 2 is the cluster resource. You might think, hey, if I set up a cluster with streaming settings, won't it just run my pipelines? Not quite. Clusters provide the compute power, sure, but they don't define the transformation logic or orchestrate the workflow itself. They're essential, yes, but they're not the orchestrators we're talking about here. Option 3, the database catalog resource, is mainly about mapping and managing metadata in your catalogs. It's great for organizing tables and schema, but it doesn't manage streaming logic or state transitions during your workflow. So it's definitely not the right tool for orchestrating streaming medallion pipelines. So what does this really mean for you as a data engineer or project team member? The key takeaway here is that pipelines are the go-to resource for managing streaming transformations in Databricks. They let you declare your workflow, define transformation logic, handle triggers, enforce data quality, and even publish outputs ready for dashboards, all in one clean managed package. If you want a robust, maintainable, and scalable streaming workflow, the pipeline resource is absolutely your friend. All right, friends, that's it for today. Remember, when you're working with medallion architecture and streaming data in Databricks, think pipeline. It's your one-stop shop for orchestrated, high-quality, and dashboard-ready transformations. Thanks for hanging out, and if you found this useful, don't forget to like, subscribe, and hit that notification bell. More practical tips and deep dives into data engineering are coming your way, so stay tuned.